My name is Sherif Zahran, and I finished my PhD in University of Calabria. It's a joint collaboration between France, University of Grenoble, Alpes, and also CI Microelettronica. And that was the part of the work that we did after the PhD. And yeah, we faced some issues regarding the bond wiring and the integration of the work that we did. Basically, we did a transition that translates the signal from WR12 waveguide to a GCBW. So at the final integration point, we needed a dummy RFIC in order to translate the signal. So we realized this back-to-back scenarios. By the way, we published this work in IEEE, and you can find the full story about this in this QR code. So the use case is like this. We have the waveguide signal entering from that side, and then translate it to the transition, to the GCBW, and then we mimic the RFIC with just an alumina board with a high dielectric constant to mimic the RFIC with the silicon. You have a dielectric as well, with just a single wire bond on top, and it's conductively glued to the transitions on below. So when we did the measurements, we found an odd result. So the S22 is different from the S11, and we are said to ourselves what could be the problem, and it should be the wire bond which is added, and it's also unsymmetric in this back-to-back scenarios. So we did a study. Usually what you find in the literature is that all the people are using the lambda/4 transformer in order to compensate this issue. But it's a bandwidth limited because it's lambda/4. So we propose here to just use a power divider, a simple power divider that can be realized on the alumina with a 2-wire bonds. And this can be good for two things. The first one is bandwidth unlimited. The second one is that you can have a less degree of tolerance when it comes to the inductance and the parasitic inductance. So here are the equations. Simply, we just have two parallel inductors, so we cut the error of the inductors in half. And we did a lot of scenarios also to study about the effect of this on the reflection coefficient and the insertion loss. And we did 100 simulations here, 140 simulations here, and we take the RMS error between them. And indeed, at higher frequency, even at the whole band of operation, you can find that there's a huge compensation when related to our proposed scenario compared to the conventional scenario. And mainly that's it. That's the whole idea about the paper. And if you have any questions, please let me know. Thank you guys so much. We should have a nice video.